Everybody hear me? Yep. Anyone thumbs up? Thank you, Renata. Okay, good. In that case, good. Thank you very much. We have our front slide there, which is mostly come up. Yes. Thank you. All right. Well, in that case, let me welcome you to the meeting. Just grab my agenda and we'll get going. We have apologies, General Secretary. I think that'll work, but.
Yes, Mr. President, apologies.
But yep.
Oh, should I be up there?
I think so. It's not going to work. It's not going to go on to Zoom from there. I'm sorry. If you're speaking, you have to speak from there.
Okay, Mr. President, apologies have been received from Chris Stockdale, Julian West, Peter Culshaw and David O'Driscoll.
And also, I'm speaking, also from Chris, my wife. She's madly busy running Scout programs at the moment.
Thank you. Right. Thank you very much. There are apologies. Any other apologies anyone wants to raise? In that case, we might move on to the minutes of the previous OGM, or Ordinary General Meeting. You'll notice those have been circulated in the newsletter. Can I see if anyone wishes to raise any issues about those? Can I also, while you're thinking about that, just check that in the meeting room here you can hear me? Is that okay? Thanks. Good. I know I've got a loud voice. They told me that at home a lot, but okay. Well, in that case, I think we might ask if anyone would move the adoption of the minutes of the previous OGM.
Could you move it from there, Nick? I should have, but I can't.
Yeah, Roy, you're moving the. I'll record that you're removing the minutes, and David Moriarty is seconding. Could I see everyone in favour, please? Thank you. I think that's carried. We'll move on to the President's report, and the President's report is in the August newsletter. No doubt you've had a chance to look at it. John Cellini will have done, certainly, as he's had a look at it. So unless there's any questions on that, I think it's fairly straightforward. No, okay. Let's move on to the General Secretary's report. Roy, I'm afraid you're going to have to pop up here to do it. It's giving us exercise at least this today. I'll mention that to you, Q.
It's always good to get a bit of exercise, I suppose. There were two major things that I just wanted to mention from the correspondence during the last month. The first is that our equipment officer, Alison Beck, this is internal correspondence to the association, our equipment officer, Alison Beck, who's served in that position for many years and quite diligently, has decided that she needs to step down at the end of this year. So the association will be looking for a new equipment officer to look after the loan equipment for the association. I'd like to move a vote of thanks to Alison, who's done that job for a long time, and we're all very grateful to her for the time that she's spent looking after the equipment. The other thing that was mentioned in a notice sent out to all members was the death of a previous member of the association, Violet Hall. On behalf of the association, I attended her funeral service at Kenmore Uniting Church on Thursday, the 4th of September. A large congregation. She was a well-loved person. As John Cellini said when he responded to the notice, Peter and Vi Hall were stalwarts of the association, and they certainly were. They were the main things, Mr. President. Thank you.
Thank you.
I move that the General Secretary's correspondence report be received or accepted.
Thank you, Roy. Could I have a seconder for that? Thank you. And those in favour of accepting it? Of course, you can challenge Roy now or later if you like on those. All right, thank you very much. We don't have the membership secretary is unfortunately not able to be with us today, but he has reported to me, and I shall report to you that the membership is 135. It's what the highest has been for a while, but we haven't had any members join or leave in the last month. But we have some member who's joined in advance, who'll be joining us in October. So it will go up next month. I think you'll have the pleasure of reporting at least one additional number next month. The technical secretary is also unable to be with us today. That's Peter Colshaw, and no doubt we wish him well. I think he must be on holiday somewhere, so we wish him well with that. And that allows us to go straight on, I'm very pleased to say, to the main item today, which I'd like to introduce to you now. I won't introduce too long because I want to hear from Vanessa, but we're going to be hearing from Vanessa on the title of her talk is Decoding Galaxy Emissions with Sparse Multi-Wavelength Photometry. And it discusses QUT's research into galaxy evolution, focusing on extracting key properties of galaxies and understanding their co-evolution with active galactic nuclei by analysing their intrinsic emissions. So I'm looking forward to that. Just let me tell you a little bit about Vanessa, and then she can come up and present to you. One of the things we're delighted to have her here is that she's a research student with the QUT Astrophysics Research Group, focusing on extragalactic studies. She began her postgraduate work at Swinburne University of Technology, which for those who've not ventured too much south is in Melbourne, and modelling the tidal features arising during the formation of elliptical galaxies through mergers. So we're really keen to hear from you, Vanessa. So if you could come up here and present from here, and you'll probably need to project your voice a bit to make sure everybody in here can do it. I've got the microphone on here, but its use is not enormous.
Fantastic. Thank you very much. Okay.
Well, at least share it, sorry.
No, I might just let you navigate your machine.
I don't like you doing it. I don't feel proprietary about machines anymore because try to know what Microsoft has done to them overnight, no doubt. Here we are. Here's your presentation. Jolly good. Oh dear. Can't read it. We just needed that, didn't we? Hang on. Can you grab your thing and we'll bring it back up? Yes, thank you. I'll just need to grab something from over here as well. Sorry about that. I can't read the presentation. Good. I'll just check that everybody can see that in Zoom. Can you see that?
Yes.
Okay, thank you. So I think you can just go on in the normal way there. Just try.
So just move along.
Hang on.
No.
Move that out of the way for the moment. Move that out. Didn't do it there, but it's. I thought I was in slideshow mode.
Yeah.
Yeah, there.
Oh, that's okay. I might just go into that. Yeah.
Okay.
Is it right? Letting you just
Or if I come out of slideshow for a moment, shall I? And then we'll.
Yeah.
I think it's doing it.
I think it's because you might be.
Yeah, no, it's on that. Yeah. Okay. Let's go into here. There. That's it, isn't it? Although for some reason it doesn't want to Spurs that, does it? Sorry about that.
That's okay.
We then just need to share it, don't we? There we are. You're certainly sharing it there. Is it up there? Yep. Okay. We're doing, I think, let's see if it'll go down. Yes, just by using those.
It's not moving here, so what we might do is just get
Yeah.
into this one.
Yeah, that'll do.
That side, and then I should be able to, yeah.
Yeah, you can get it there. Okay, thank you. Sorry if it's a bit fiddly today.
No, that's okay. All right, so I think we can get started. All right, fantastic. So first of all, can everyone hear me properly, both online and obviously here in the room? I don't always have a big voice, so I've been told to try to speak louder. So if at any point you don't hear me properly, please let me know. For those online, I do apologize. I think you're getting quite a good shot of my nostrils, so it's definitely not the most flattering part. So first of all, thank you very much for having me here today. I'm a pretty recent AAQ member. Myself, I joined in May, I believe, and I do apologize for not having been present a bit more in the last sessions. I was actually away in Europe. I was at the European Space Southern Observatory headquarters in Germany. So obviously I just got back just a few weeks ago myself. So it's a good opportunity for me here for today for me to meet some of you obviously in person, and hopefully I'll get to see more of you in the future. So as per the lovely presentation, so thank you very much. Obviously, as you heard, I'm currently a research student at QUT as part of the QUT Astrophysics Research Group. Here are some of our major affiliations. So obviously you can see yourselves here, the AAQ, sorry. And I'm also part of a very large cohort, international cohort. We are currently 400 scientists linked together all around the world, and we're working on the evolutionary map of the universe survey. I will briefly touch on this survey, but not to a great extent. So if you have any questions, obviously, please let me know. This particular survey is currently conducted in Western Australia, so it's underway with the ASCAP. This is the ASCAP EMU survey, and it won't be going until 2028. So again, I'll be discussing this very briefly. So obviously today I'll be discussing a part of my research. Again, if at any point you have any questions, please let me know, and hopefully I'll try not to bore you too much. So again, let me know if you want me to stop at any point. All right, so first of all, I would like to present to you our team just very briefly. One of the things I forgot to mention is that aside of my research, I'm currently a program officer at the Sir Thomas Brisbane Planetarium, and something that I have recurrently are families that come to us and actually don't know that QT exists. So it is a good opportunity to obviously pass it on to you if you have children that are interested in astrophysics, or people who want to redirect their career. Know that obviously UQ is a fantastic foundation, but QT also exists, obviously. So at the moment, at the head of our research research group, we have two academics. The first one is Rosanna. I believe you know both of them. Rosanna used to be at UQ and she joined us about a bit more than a year ago. Now she's working on dark energy and gravity, and to be very precise, on modified gravity. Now it's a bit dark magic to me, so I won't insult her research and I won't talk about it. But if you have any questions and you wanted to discuss further, please contact, obviously you're more than welcome to contact me and I'll redirect it to her. And then my principal supervisor is Michael Kelly. Michael Kelly is essentially focusing on galaxy evolution, but mostly on the impact of supermassive black hole and their feedback on the evolution of their host galaxies. So this is obviously orienting our research group towards this particular part, and a part of my research is going to be to obviously classify these supermassive black holes that are currently feeding. So again, I'll touch on this very briefly, but I just wanted to mention or to introduce to you our two supervisors. And our group is very diverse. We have here an example of a few current and past research students. Our research topics will vary quite greatly, from the refinement of distance measurements, and that's my case. Or we also have, as you can see, Jess at the top, who is currently designing new diagnostics to classify AGN. And we also have people working at a more galactic ecosystem level. And we have, for example, Brianna, who has explored the influence of dust on galaxy evolution. So again, we have quite a wide research, but all of this is coming to basically the same goal. As you can now understand, QT is solely focused on extragalactic astrophysics and cosmology through Rosanna with dark energy. And our extragalactic research is essentially focused on galaxy evolution and the interplay with their supermassive black hole. And in terms of method, we're non-discriminatory. We'll pretty much use everything, every mean that is available to us. So it starts obviously with very deep photometry, very precise data. And then, unfortunately for us, we don't actually get to do a lot of telescope time, so I never really observe. The only time I get to touch a telescope is either myself in my backyard if I have a little bit of time, or obviously at the planetarium. So my work is 100% theoretical, like most of us, and so it means that 100% of the time we are pretty much stuck behind a computer. It's not very romantic, but it does a lot of wonders. And again, cycling back to opportunities, we do have at QUT quite a few vacation programs, and that is quite interesting for families that have children that are currently transitioning from high school to university. So again, if you have any questions about this, please let me know. I'm not advertising QUT. It's more about discussing the options of studying astrophysics here in Queensland. All right, so let's get started, and I'm actually going to turn to you here. It's a shame I had some cute videos playing in the background. So this background, it was supposed to be animated, and I can see it's not playing very well. But I'm just going to give you a few moments. I probably won't be able to read the chat online, but I'm just going to turn to you here, people present in the lecture room, and tell me, how would you describe a galaxy? So pretend that I have absolutely no clue about what a galaxy actually is, and how, in a few words, would you actually encapsulate the complexity of galaxies? So what would you say? First thing, what would you say to me to explain what a galaxy is?
An island universe.
An island universe. I love that. That's absolutely stunning. What else? So
Fuzzy cloud.
Fuzzy cloud in the sky. Okay, so what would... Fantastic. Okay. And what else? Any other attempt at answering?
Made up of hundreds of millions of stars.
Made up of hundreds of millions of stars. Yeah, absolutely. We also have actually clusters or very small galaxies that can only contain a few thousand stars. So obviously we have here a cluster of stars that can be composed of obviously a few thousands up to a few hundreds of billions of stars. And it's not just a simple cluster, it's an open cluster or globular cluster that you will find within other galaxies. Obviously, they are standalone groups of stars, okay? So fantastic. Now, obviously, we also know that we have various morphology. So we know that they vary in size, mass, and morphology and colors and so on. And we'll get to this in a moment, but we're just going to backtrack a little bit. I'm pretty sure that everyone is very familiar with this diagram. It's well seen, well known. It's quite a fantastic diagram, actually. It's encapsulating 13.7 billion years of cosmic evolution in just one slide. I'm not going to go through all of it, but obviously we have the Big Bang, we have other densities leading to the formation of the first galaxies and the first stars. And this is happening somewhere between 200 to 400 million years after the Big Bang. But the part that really interests me currently, what interests our team is that turning point that you can see here at 2 billion years. So about 10 to 11 billion years ago, we're looking at a time that is called cosmic noon. And at this point, we're observing a peak in star formation and galaxy formation. And we also know that at this point, the supermassive black holes inside of these galaxies were growing more rapidly. And so it is likely that at this point, their feedback is now starting to influence the quenching or the evolution of the stars inside of these host galaxies. So it's a real turning point. It is a snapshot of the universe at which part it is actually going to influence the galaxies that we see today and their behavior, obviously. And you're also probably being the astronomical group that you are very familiar with the Hubble tuning fork. It has for a long time, especially in our hierarchical cosmological model, you know that supposedly large structures have formed from the aggregation of smaller structures. And so for a long time, this fork has been seen as an evolutionary track. We know today it's probably a little bit too simple, but we're still using it as obviously a good morphology classification scheme, okay? So you can see on the left-hand side, we have ellipticals, which are the most massive galaxies that we observe today. And then obviously it's forking out. We have the spiral galaxies without bars and the barred spiral galaxies just below, which includes the Milky Way. So we know all this. How do we know all this? We know all this because obviously in our local universe, we have this ability to observe them directly. So you're looking at this absolutely stunning image. It's very well known as well from the James Webb Space Telescope. It contains quite a plethora of morphology of galaxies here. We have essentially only local galaxies here. The closest one is 7320, just at the top, but they're all very close to us in terms of cosmic distances. Now, from what you see here, can you identify some morphologies that you would recognize and that you would be happy to tell me about? So can you recognize an elliptical galaxy up here? Yeah, which one?
Left.
Yeah, the NGC 7317. Yeah, we also have interacting galaxies just below. We have a disturbed barred spiral galaxy, NGC 7319, and obviously at the top we have actually another edge-on disk galaxy. So at a glance right here, you can quickly tell me what type of galaxy we're looking at. Most likely, if we study a little bit more about their luminosity, we'll gather their stellar mass and their obviously from their angular size, we'll know how big they are. So that's fairly easy, right? And we can even look at the colors and probably see whether they evolved. We also see the ones that are currently interacting with one another. Now, if we're lucky, we can look at more distant galaxies that have been magnified through gravitational lensing, and that is due to the interference of a black hole, or in that case, particularly a globular cluster in a way. So it's going to magnify these very distant sources in the background. You can see this beautiful arc just on the outskirt here. So this is another way that we have to look at the distant universe. But let me show you what I actually see. And unfortunately, it's nowhere near as straightforward. Okay, so now what about that? First of all, can you tell me how many galaxies we're looking at? Absolutely not, right? So right now you have about 70,000 sources, and these are the sources that I'm currently working with. So as you can see, these are HST Hubble Space Telescope legacy fields, and we have overlapped. So these are parts of the sky that have been very well surveyed through many different facilities, both in space and ground-based. And so we can gather these different observations at different wavelengths, and we are going to overlap them to gather as many data points as we can. So we cross-match the sources and we gather as many data points as we can. So up to, in CDFS, for example, the left-hand side one, per sources, we have up to 43 data points. So at this point, we have a lot of information for these sources. And this particular survey that I'm working with is spanning UV to all the way to far infrared wavelengths. So we have a lot of information about these galaxies. And this is quite essential. I've put the moon here for a size reference. So they're a pretty relatively big field for pencil beam observations, but obviously we want to go quite deep. So we either go deep with observations or very wide, but at the moment we can't do both at the same time. So we use these particular deep fields where we have a lot of photometry available to us to calibrate our pipeline so that we can get ready for the millions of new sources that will come from a survey like EMU, for example. And again, we're spanning UV to infrared. This is very important, and this will become more important as we go through the conversation. Did you have any questions so far, or no? That's okay. Fantastic. So I'm just going to carry on. Now, just to give you a bit of an idea, this is the EMU survey. This is the map of the EMU survey. The green tiles, they are now more because this is a previous, an outdated picture of the EMU survey. But the EMU is going to survey the whole southern sky up to 30 degrees north, okay? So obviously a lot of the sky area has not yet been surveyed by other facilities. And this is really our problem at the moment. Now, to give you a size reference of our current, the survey, the Z-Forge survey that I'm working with, just one of these stars that you saw here is actually bigger than the current survey that I'm working with. So this is the immensity of galaxies that we're looking at and that we will receive. So within the EMU, which will run until 2028, we anticipate to have about up to 50, maybe 70 million new galaxies. And as an example here of what we mean by sparse multi-wavelength overlapping data is that obviously these facilities will run a certain amount of time within covering a certain part of the sky, but it's not homogeneous, okay? It's going to be very, very different. And so from one side to another, we may gather, I don't know, maybe 13 photometric bands per sources at the very, very best. So from my 43 to 27 photometric bands, now I need to make sure that I understand the kind of science we can do when we reduce this by half or even 3 times or even maybe less per sources, because these sources that we're currently looking at with EMU, they are radio sources, which means that per source, I'm going to only have one data point, okay, in radio continuum. So this is exactly where my research is fitting in. I have in the past year solely focused on understanding and assessing how reliably we can derive photometric redshifts and also stellar masses and star formation rates, but using as little amount of data as possible. And again, trying to get to squeeze really as much science as we can out of maybe 5 or 6 data points. All right, so you may wonder, for those who are familiar with photometric redshifts and spectroscopy and so on, you may wonder why we're focusing so much on photometric redshifts. So spectroscopic redshifts are the most precise measurements that we get today. Unfortunately, they are extremely time consuming, and to get a very high resolution spectra from an object, unfortunately, we're limited usually to bright galaxies, blue galaxies, and relatively local, I would say. And so the only alternative that we have today to actually get redshifts for fainter sources is photometric redshifts. Another very convenient element for photometric redshifts is that they are very efficient in terms of telescope time, and we can derive a redshift for absolutely every source in a deep imaging survey. So just as a reference, using even our best spectrographs today for a survey such as DEEP2, a little bit of extrapolation to get the same result as we would do with photometric redshift methods, it would take 16 up to 16,000 years of continuous integration time to get the same results than we do within a few hours with our computers. Okay, so this is really the advantage of photometric redshifts here. All right, so let's dive a little bit into the procedure or the technique that I'm using. So there are various ways to derive photometric redshifts. Pretty much these techniques are divided into either machine learning or, in my case, SED fitting. You are probably familiar with SED. It stands for spectral energy distribution. This is the distribution of energy as a function of wavelength or frequency. And obviously the fitting is a statistical procedure that matches the theoretical models to obviously our observed data. And in principle, this is a very, very simple technique. You can see here we have a set of observed fluxes. I think here we have probably nearly 30. And then we are going to compute synthetic models. And then eventually from these models, it will compute some modeled fluxes. And eventually it will match these fluxes to our observations. And at this point, it's going to select the best parameter set that corresponds to what we're observing. So at this point, obviously, we can derive the redshifts and many other important parameters. So again, in principle, it's a very simple technique. But now we're going to dive and dissect a little bit these galaxies and understand that it's actually not that easy to create these synthetic models, okay? So this is a beautiful, again, resolved galaxy. Inside of a galaxy, we have the obvious. We have stars and old stars. Stars will emit anywhere from UV to infrared or near-infrared wavelength. We also have a little bit of dust, and that is a problem because dust will absorb the light and re-emit in near-infrared and infrared wavelength as well. And obviously, we have a lot of gas and we have star formation regions. In these star formation regions, we have very young stars. They will ionize the gas surrounding in their surrounding, and this will produce a continuum and also nebular emission lines. So we need to account for this. This will naturally shape the SED of the galaxy. And then to complicate all of it again, we have this supermassive black hole at the center, and when they're feeding, this is when we call them an active galactic nucleus, so AGN for short. And when they're feeding, they're pretty messy eaters, so they create a lot of different processes in their surrounding, and these different processes will emit various types of radiation from X-ray all the way to radio. And so we really need to know when we observe a very luminous galaxy, is that luminosity coming from the feeding black hole at the center, which is actually not nuclear, it's not nuclear powered, or are we looking at a galaxy that is actually distant but star forming quite actively? And so it's important to disentangle the two. All right, now, what does it look like at a spectrum level? So obviously, you know that even at a star level, we are, the first thing we are going to compute is the stellar component of the galaxy. And yeah.
Vanessa, you may have to repeat the question.
Sure.
Could you explain what the y-axis represents?
The y-axis, yeah, this is just, as you can see, it's an arbitrary unit. So this is just what you would imagine in terms of fluxes, the energy of the spectrum, yeah. So at this point, we have just a dummy set of spectrum of these stars. So we have just an arbitrary unit, yeah. You can have them in milligenskis, you can have them in angstrom, whatever suits you. Okay, so, yes?
How is that?
How is this measured? So again, we're just doing this through broadband photometry. So we're just observing these sources through broader filters, so as opposed to spectrographs. And we're gathering these lights. So depending on the filter is only going to gather a certain part of the spectrum. In this case, again, this is a dummy representation just to show you what the spectrum of two different types of stars would actually look like. But yeah, so we're gathering the photometry of these galaxies through different types of filters. And then for us on our side, it's going to look like a little bunch of units of energy that is given from this particular galaxy at a particular part of the spectrum. Yeah. Just to move on from this, here again, we have a perfect representation of how two different stars. So you look up at the night sky and you have blue stars, red stars, and so on, different spectral types. And obviously, it means that their signature is going to be to look very different. So how do we account for this in our models? Well, we use building blocks. So you have to imagine we basically tasted a cake. We have a cake. We just don't know how to make it. So we're basically going to throw a lot of different ingredients and let the model tell us which were the best ingredients to use to recreate the cake that we've just observed. It's a pretty bad analogy. I love food way too much, but you probably can understand what I mean from here. So SSP stands for single stellar population. And what they are is the little building blocks that are idealized models that will take a type of stellar population, which they have the same initial chemical composition. And then it will trace how these evolve and change depending on their age, at different ages. So how do their spectrum evolve through time? And then we're going to do this for one type of population, another type of population, and so on. And then eventually using what we call stellar population synthesis framework. It's basically going to combine and reintegrate all of these little building blocks, assuming a particular star formation history. So that star formation history here that we're going to input in our model is also extremely important. Now, again, these are just basic representation, but what we're doing here is that we need to tell our model how these galaxies are actually evolving. Are we looking at galaxies that have experienced many starbursts for a long time? Or instead, do they form their stars over a very long extended period of time? So we do instruct our model that it may be, in fact, an extended star formation history. It will assume this type of star formation history, and then it will combine these building blocks, and it will evolve the stars within these building blocks accordingly. And so from this, we have the full total stellar emission. This is our complete stellar component of the galaxy now computed. It is banked, and it has created millions of models against which it can be matched. Now we're going to move on and we're going to do the same with these other components. As I mentioned before, in star formation regions, we have very young stars. These young stars are producing a lot of UV photons. And what's going to happen is it's going to ionize the interstellar medium, and the recombination is going to produce nebular lines, nebular emission lines that you can see quite drastically there. This is shaping the, oops, yes, sorry, did you have? No, sorry. This is going to shape the final SED, and these particular lines are very interesting to us. We are looking at anchoring these particular lines, especially when we're starting to derive redshifts. So this continuum is very important, and these nebular emission lines are also very important to take into account. Then we're moving on to this famous dust attenuation. This component is extremely important to us because the dust is going to do the same thing as the redshift is doing. It's going to redden our galaxies. So now the question is, if you look at a red galaxy, are we looking at a galaxy that contains a lot of dust, that contains a lot of evolved stars, or in fact is redshifted? So you can see our problem here in the necessity to input a lot of different dust attenuation possible so that the models can actually match and make the difference between the three. And this is the full integrated SED pretty much. So if we resume all of it, now you understand the importance of gathering photometry through different wavelengths, because each wavelength is dominated by a different process inside of the galaxy. So again, the UV regime is essentially dominated by young stars. And by extension, it's going to actually allow us to derive star formation rates. Then the optical to near-infrared regime is mostly dominated or given off by evolved stars, and this will help us determine the stellar mass. And then moving on to the mid-infrared regime, we're looking at dust and little carbon molecules, and then the far-infrared and sub-millimeter component is usually hot and cold dust as well. So we can get metallicity and dust mass and so on from the galaxy. So now we have a complete story of our galaxy. And from this, if it all matches really well, we can tell well, yes, this is a massive galaxy. It is a star-forming galaxy. It is this big and it is this far. Now that's easy, right? It sounds relatively easy, but we have other things complicating it in a way, and obviously this is the redshifting element. So hopefully, I don't know if I can play this. Oh, what a shame. I don't think I can play this little video. Oh, yes, I can. So we have an SED redshifter just on the side here. So you know that the universe is expanding. So that expansion of the universe, this is what these redshifts are. Redshift is telling us how much the light has been stretched due to the expansion of the universe. And so obviously it is a proxy for distance measurements. To give you a bit of an idea, at redshift 1, the size of the universe, or the universe, is about half its current size. And our turning point at cosmic noon that I was talking about just before is at about redshift 1.5 to extending all the way to redshift 3, okay? And as obviously you now understand, these distance measurements are essential before we derive any other parameters in a galaxy. Because again, if we are looking at a distant galaxy, it will look redder by nature, but it is not an evolved galaxy or a galaxy that contains a lot of dust. So before we can derive anything, we absolutely need to know their, or globally know their distance to us. And so, excuse me, going back to this full set that we had before of a nicely matched model, you can see here we have at least nearly 30 data points. So what we're looking for, just like we would do in spectroscopy, we're looking for very important features, spectral features inside of the spectrum that can be, again, the Lyman continuum, or it can also be the Balmer break. And we have a better chance at sampling these elements or these spectral features if we have more data points. But now if we only have a few data points here and there, as these features are moving, as these galaxies are being redshifted, obviously we're losing these anchors. And so if we don't sample the proper part of the spectrum, we're actually not finding these spectral features anymore, if it makes sense. So this is a challenge here. And so this has been a part of my pipeline. I've obviously tried many different photometric band configurations, and mostly what I've been trying to do is not only assess how little we can use, but also which one were the most important to sample. So within our range, within our redshift range, what are the photometric bands? What part of the spectrum do we actually need to sample to be the strongest and to provide the most information that will be valuable to photometric redshift derivation? And this is an example of a real city, of a real galaxy in a CDFS field. You can see here we have all the data points. So I've got about 43, I think, on this one. And they're very nicely matched. They match the model. They match my parameter space. So I can really tell. In fact, you can see that the photometric redshift has been derived at the top. And this galaxy is at a redshift, of 0.6. And then we match this against spectroscopic redshifts. As I mentioned before, they're extremely precise. So ignore the little side note. I used this particular slide at university a while back. But what we're doing is we're matching our photometric results to spectroscopic values, which are known to be very precise. And so obviously you can see we have a few outliers that eventually we will have to address, but globally it's following a fairly tight relationship. So we know that our parameter space is valid. And from this point on, I can reduce the amount of data that I give it. And this is what you see here now from the 43 data points that we had before. And I have only about 6. And as you can see, they're extremely well spaced. And so they are still constraining that model really well. And so even with 6 well-spaced bands, it turns out I still can actually match my models to my observed data. So this is important, but as you can see, they're not randomly spaced. They are sampling some very important element of the spectrum. And so here I'm giving you the most catastrophic failure that I've had. And this is, again, very important to notice. But as I mentioned before, within our redshift range, what we know for certain is that with that particular parameter space and with this particular software, if we don't have near infrared data, we simply won't have accurate results. So it's simply impossible to derive accurate redshifts. This is the red part of the diagram here, of the plot, and it's erratic at every level and at every redshift. Globally, and I'm not going to go through all the results here, but globally we find that if we use a good balance of about 5 optical photometric bands and 2 near-infrared bands, usually we get some pretty good results across all parameters. Now, galaxy properties, I'm going to touch on very, very briefly, but the main goal of testing them was to know if I do select a certain type of bands or photometric bands, are these valid for the redshifts, but also for deriving stellar mass and star formation history? Because if I can only derive one thing, it's probably not very interesting. So this is going to guide, for example, follow-up observations. If we have a part of the universe that's particularly interesting in the southern sky and we only have radio data, what is the next priority to actually observe? I'm just going to get past this fairly quickly because we have discussed this quite extensively, but you now understand why this redshift range is very important to us, because this is a transition from these very active star-forming systems all the way to the quiescent systems that we observe today. So again, a real snapshot of the universe at a decisive time that shaped the behavior of our current universe. And we're looking at stellar mass, obviously, which is tracing the full content of the galaxies. And it's going to tell us how and when they acquired most of their stars. And again, it's happening essentially within that redshift range. And then we have star formation rates. This is the second part that I was trying to obviously try to derive. And this is basically the rate at which a galaxy has transformed its gas into stars. So again, that is quite an important component to derive for galaxies. And so I'm not going to go through this diagram to a great extent, but you can see an example of a few bands. Most of them are relatively tight. So this is the median stellar masses that we're looking at for different band configurations. But all you can see is that the red ones are systematically, both in stellar masses and in star formation rates, systematically the ones that will give us the greatest error and the greatest deviation. So these are the configurations where we do not have near-infrared photometric bands. And so what it means in terms of relationships, so we have many, many different relationships. We know that these are very much interlocked with one another. Star formation rates and stellar masses is going to give us a very famous relationship that is the main sequence. So it's telling us how and how fast these galaxies have grown. And you can see these different colored bands here are representing the main sequence of these galaxies at different redshifts. And you can again see the red dots right in the middle are obviously very deviated from the blue line, which is the main full band results. And so what it's going to do at this point, it's pushing all these sources above, or most of them above their main sequence. And what we would say from this is that basically these systems have to be starburst systems. They are not regular star-forming galaxies. So all of a sudden, we actually have a whole bunch of star-forming galaxies, but because we have inferred the wrong stellar masses and the wrong star formation histories, now we're concluding that we're looking at starbursts, and that has a heavy consequence on the cosmological models as we know it today. So this is why it's so important to derive these elements so precisely. All right, so the last little bit that I'm going to touch on is this famous AGN. It is quite a complex system. The central engine, as I mentioned, eats in a quite messy manner, and it's going to create a whole ecosystem around its own self. So we have the torus around that looks a little bit like a donut, if you will. Sometimes we have these jets, and when they hit the intergalactic medium, they create a lot of energy, and this is what we catch, obviously, sometimes. If these jets are unfortunately aligned with our line of sight, we can't actually see them. It doesn't mean that they're not here. And so what it's going to translate in a bump in the radio wavelength. So we need to know where this is coming from. So this is a part of my research for the next few years. Hopefully, I will actually focus essentially on integrating these templates of AGN inside of my pipeline and understand how it affects redshift derivation and all the other properties that I mentioned before. Just to give you a bit of an idea, this is how bad it can get. So here in the orange side, you can see the AGN templates are added, and you can see that we can actually obtain accuracy that is tenfold better than when we don't have these AGN templates, when we have AGN sources. So not all of the galaxies are going to be AGN sources, but when you look at a part of the sky, you have no idea to begin with what kind of galaxies you're looking at. So you need to make sure that in your ingredients that you've input in your models, you take into account that as well as all the other elements that we mentioned before. And again, I've just mentioned before that this is essentially the next phase of my research. So maybe you'll have me again in a year's time or so, and I'll be able to present more about supermassive black holes. And one of the main elements that we're trying here to do is not only to see how it influences how we derive the properties of galaxies, but we're also trying to understand how the feedback of these black holes have actually influenced the evolution of these galaxies. You'll have different opinions on this. Some teams will say that it is sparking, inducing star formation, and other teams will say, well, no, actually we can observe that it's quenching star formation. So again, maybe we're both wrong and maybe both a little bit right at the same time, but we try to understand, obviously, this particular influence. And that's pretty much it. It's bringing me to this conclusion. So photometric redshifts are very important. They are next only solution to derive distance measurements from these very, very, very large amount of galaxies that we are about to survey with surveys such as EMU. And then reliable photometric redshifts can be obtained with probably as little as about 7 photometric bands if we choose them well, at least within a range of 0 up to 2, redshift 2. Stellar mass and star formation rates estimates are going to follow the same trend. So it's very positive. It means that using the same model, the same parameter space, software, and filter set, we can actually derive quite reliably the photometric redshifts in these 2 parameters. And again, the next phase of our research is going to be integrating these AGN models inside of the galaxy templates. That's it for us. So I'm just going to leave it to this pretty much. This is our team. We do a lot of outreach events. As you can see, we're quite a dynamic team. Please feel free to join us at any point. And again, communicate with us if you have any questions, even later on. I'm an AQ member, so I'm on the mailing list. So please feel free to have a chat. And that's it. Thank you. So this was supposedly animated. So I do apologize. My all flashy animations did not come through, but hopefully it didn't deter the quality of the slides. So if you have any questions, I'm right on time. I was really happy. I was trying to be right below 45 minutes. So I'm right on time. If you have any questions, please let me know. Otherwise, I'll let you move on. Yes?
Can I come up and speak into the...
Yeah, of course.
Thanks, Vanessa. Could I ask you a very basic question, please? I'm not sure that I understand how you calibrate the photometric redshift. Is it that you look at the profile of photometry in galaxies at various redshifts?
That's correct.
And therefore you can then determine in the test population what the redshift is?
That's exactly right. Yeah. So that's not a simple question at all. It is a very important question. And in fact, I did not mention this, but this is very valid. So once we have created all these spectrums, we basically, just to give you a bit of an idea, when we say we try to match a synthetic model to the observed fluxes, before to do so, the model that we're talking about has computed probably up to 5 million different synthetic models, okay? So all these ingredients that I've given to my software, it's now going to create one synthetic spectrum for every possible combination that it has been given, okay? So eventually, among these 5 million different spectrums, one of them is most likely to match what we're looking at. And so it's going to make that particular difference. It is easier to make the difference of a redshifted galaxy or dust galaxy, again, if we have particular spectral features, because the spectral features will change in position. At a position, we know their initial rest frame position, and it's going to change with redshift. So if we can catch these spectral lines or spectral features moving, we know that we're not looking at dust here. We're looking at something that has been redshifted. So yes, it's very valid. We do look at the spectrum, and then they are redshifted within a redshift grade. And then eventually it will match all of this and then find the most appropriate parameter set. So among our parameters that I will input, a part of it is going to be a very fine redshift grade. So I'll give it many different redshifts at which it needs to take all the models that it created and redshift this at every step that I've given it to. If it answers your questions, hopefully. Yeah. Did you have any other questions?
The software, is that all developed at QED, or are you using international software?
Correct. So the question is the software built at QET or internationally made? This one in particular is from an international team in France. It's unrelated to me, although I am French, as you can hear, but the particular software is called CIGAL. It stands for Code for Investigating Galaxy Evolution. So we have different types of ACD fitting softwares. In fact, we have many of them. This one was chosen for us because it has the possibility to integrate AGN templates inside of it. So a lot of them actually don't have that option, and they will only focus on particular parts of a galaxy. This one is the most complex, the most complete, if you will. That's it. Unfortunately for it, it's actually not the one that is it's not optimized for redshifts. We have another software called Easy, for example. This one is optimized for redshifts, and you would think, well, since we're doing photometric redshifts, we might as well use it. But this has no potential for integrating AGN or anything like this. And it's pretty poor when it comes to deriving other properties. So yeah, but again, we will investigate probably different types of different softwares. But this one is not made at QET, no. All right.
We might just, Vanessa, if I could.
Yes.
Check if there's any questions online. Yeah. I think we've exhausted the questions in the lecture theatre. So can we just see if there's any questions online?
Maybe there's some.
Stop sharing.
We might stop sharing. Yes.
I'll let you.
Oh, you can stop sharing. It's all right. No, that's just like we can end your slideshow, can't we, as well? So.
Of course, yes.
There we go. Thank you. So are there any questions?
Maybe in the chat room?
Yeah, possibly, but I was because people can unmute themselves and ask the question if they like. So I can't speak today because I'm on, oh, that's not. I can't see any questions online. Any further questions? Any questions anyone would like online?
Yeah, I got a question. It's Stephen here. How you doing?
Right.
Just curious about with constellation networks and the increasing number of satellites, can that affect any of the measurements that you're doing with redshift?
Yeah, absolutely. Yeah, absolutely. So I'm definitely not going to get political today, but we definitely have our own opinions on the current phase of the new space age. So yeah, it's certainly, it came to a point where it was concerning for programs such as the LSST, where they were concerned that they would actually catch more near-Earth satellites than they would catch sources in the background. Now, there has been some very good agreements with, I believe, people such as Elon Musk to make their satellites as dark as possible. But yes, eventually, unfortunately, we do have, though, a very good way to determine whether we're looking at a satellite, obviously, or a distant source. But if it continues like this, yes, the interference from this is definitely going to be quite impactful. Yeah.
Any other questions online? Okay, thank you. Vanessa, can I thank you very much for your presentation? It was tremendous. Thank you very much. Let's join in thanking Vanessa.
Thank you.
Excellent. Well, thank you very much, and apologise for the technical glitch at the beginning there. So we're going on now to the section director's report. Yes, I see there lots and lots of congratulations there for a great presentation. We're going on to the section director's report, and I know that Julian, who's the, I think, section director for spectroscopy, can't be with us, but David Moriarty, our former president, can indeed be with us, and I think he'll therefore be talking to us. I'm just going to try and bring up his presentation. Somewhere there it is. Bear with me. That looks like it. It's on the slide sheet, and then share it if I can. It's on there. Okay. I just need to find the main bit. There we go. That needs to go. Just a second. And we'll find Zoom. There we go. And share it. That's you, I think, isn't it?
Yes.
No, that one.
Wait a minute, I've got to get closer. I should get my other glasses.
There we are. I think you're up. Can you see that online?
That's it. Yep.
I'm just checking people can see it online.
And is that a mouse pad?
Here's a mouse here.
Good.
There's a mouse there.
Good. Okay.
Anyone, I haven't had anybody responding yet to say if they can see it online. Yes, you can. Thank you, Robert. Good. All right, over to you, David.
The microphone is
On the
on the laptop, not that one. Okay. I'm going to start just with a brief introduction. We heard earlier we've got quite a lot of new members, and I haven't talked about what I've been doing for a little while. So I thought I'd just go back to the beginning. As a microbiologist, I started really wanting to do research in astronomy quite many years ago, and Arthur Page kept saying to me, you've really got to do some research. And as an amateur, it was difficult, particularly when I had lots of other work to do and traveling a lot. Anyway, I started observing eclipsing binary stars with my telescope, and I gave a seminar here 5 years ago, in 2015 to the Astrophysics group. And I said to Michael Drinkwater after it, well, those light curves are very nice and times the minimum, but to be any use to astronomers, they want to know how massive the stars are. And for that, we need a really big telescope with a spectrograph. And he said, oh, yes, no problem. UQ's got a partnership with ANU and the wide field spectrograph at ANU. So write a proposal. So for me, first time having to write a proposal for looking for time on an astronomical telescope, but fortunately he and Sarah Sweet, who was his PhD student originally, and at the time we started this project, she was a postdoc at ANU, so they contributed. She told me important things such as to get the spectral type of a star, you've got to have the calcium 2 lines down in the far blue. It's things like that that I didn't really know about. So I wrote a proposal, they modified it, and we were granted 3 nights of time on the ANU telescope. And I had to fly down to Canberra so that she spent 3 nights then with us, training me in how to use it. Then after that, there were lots of other eclipsing binaries I wanted information on. So I then wrote proposals, and Michael Drinkwater helped initially. And over the time from then until 2021, which I'm going to talk about now, we had about 45 nights observing, and roughly the same number probably with cloud. I can't remember exactly, but clouding was quite a problem. So for the observing, the wide field spectrograph, I just go back. Which way? How do I go back on this?
Second one down. Down on the right-hand side.
Ah, sorry, I wasn't watching. I was looking at this thing. No, it's going forward. We go back. No, it's going forward.
Can you use the arrow keys on people?
This is not a Mac. It doesn't work properly. Nick, can you make this go back to the beginning for me?
Possibly. Okay. Which one did you want?
Well, let's just start with the first one.
This one?
Yes.
Presume we're on that. Let's just try it.
There's not showing there.
No, okay. I'll have to come out of it. Get rid of that. And stop. Okay. Here we're on the first one. We'll just bring it up and then share it. Okay.
Is this still showing screen share for the people online?
I'm just checking. I don't think so. Sorry. I think that's the one there.
That's the one. Yes.
That should now be sharing,
Okay.
but it's okay. Participants can now see your presentation. Do you want to stay on this slide?
Yes. Well, just to start with, I just wanted to point out with.
I
this
should
one,
go down that way if I were you. Just
how do I change it then without? So that's the next one coming out.
oh, okay. It's not coming up there. Okay. All right, we're going to try and bring it out. I'll bring it up first in a different way. See if we can do it this way. But that's you, isn't it?
That's it. Yeah.
I think you can now just go backwards and forwards like that.
Okay. Using those arrows.
Yes, the arrows there. You
Okay.
go all the way through it now.
Okay. Thanks. Thank you. So I just wanted to point out with this spectrograph that there are two cameras, red and a blue camera. And for the getting enough spectra for doing radial velocities, we use the blue end of the spectrum, and we also have to use the red side of it. So anyway, after those first 3 nights, the rest of the observing we did at home, and we had various students at times coming, but mostly Chris and myself did the observing. So that's our observing room at home. And the last time we observed there was in May 2021. And I'm going to be talking about what some of the star that we observed between February and May 21. UW Virginis, it's fairly bright, V magnitude 9, and it's an oscillating algol type. So it was described as a single line binary. And like many of the other very close binaries we'd observed before, I was told before I started, oh, you won't be able to do any radial velocities on those because the secondaries are all too faint. Anyway, there is a way around it. And it involves a program called using the broadening function developed by Rosinski about 20 years ago. And he was working on very close binaries, contact binaries. And Pilecki in Poland wrote a program, complicated Python-based program called RaveSpan, radial velocity spectral analysis. And he built the broadening function into that, as well as the common cross-correlation function method that many astronomers use. And we tried the cross-correlation method first. And with several of the close binaries, we could not get the spectral lines and any radial velocity for the secondary components. But I worked out a way with RaveSpan how to do that. So this one here is the one I want to talk about tonight. So the spectrum that I looked at, I shaded out the Balmer lines and the far blue, because with a very late K-type secondary, which is what was expected, having very bright lines would make it hard to see. So by analysing spectra in these two regions, we got quite good results. And for a typical curve, radial velocity curve with a broadening function. And it shows the secondary component. So that's the first time that we had information about it. So the analyses that I did I started working on this one late last year and early this year. And the first set of analyses, I ran several iterations of the RaveSpan program, and it ended up where I had told it to start with to work on a system velocity of +22. So that's this volume, so the whole system was moving away from us at 22 kilometers a second, according to Gaia, and in fact to much older spectra as well. And velocities there for the primary star, 45 kilometers a second. The secondary was racing around the center of gravity, 197 kilometers a second. And the actual period is 1.8 days. So these two stars are very close to each other, and obviously a lot of interaction. And so that gave a mass ratio of 0.23. And then I sent that to our colleague at the Çanakkale University in Turkey, who was doing the actual orbital modeling with light curves from TESS. And he said, well, mass ratio 0.3 just doesn't work properly. He said the best result would be if you could get radial velocity showing that it was actually 0.29. So I had to work out why, when this program that had worked quite well with a lot of other stars that I've been working with, gave a result that didn't seem to fit with the modeling done with the TESS light curves.
David, just sorry to interrupt.
Yes.
In Zoom, we're not seeing the slides change. We're still on the first slide.
Oh, okay. Nick, what do we do? I got it. It's showing on here, but not on there, because I can see it on that screen as well.
Yes, it's coming up there, all right.
It's coming up in the room, but not on mine.
I think you might be sharing the wrong window.
Okay. I'll get rid of some of these. We'll have to start it again. I'm sorry. Let's just get rid of some of the different things on here. Do we have one there? No, just that Zoom, isn't it? Yeah. Now let's try it again. Here you are, there's only one of them there. There. Okay. Can you now, I'm going to move it on. Tell me if it's coming up for you.
We don't actually see the slideshow. We see the coordination screen.
We're seeing the presenter view.
Okay.
Seeing the presenter view. Oh,
Well,
So we're probably not
or
going
the editor view.
yeah. We're probably not going to be able to fix this in any reasonable time today.
Okay.
well, how did
Um,
Vanessa?
we were doing it earlier, but just a second. I'm just trying to find the right.
I think you need to start sharing after you started the slideshow.
Yeah, I think so. Okay. Let's just stop the sharing. Is that what you were doing?
Yeah, maybe stop for now and then
Yeah,
start
start
again.
again. Yeah. Okay, that stopped anyway. Okay. So if we start sharing after we've started the slide view, that should pick it up, I think. Okay, and then let's do the side view. Okay, we're on that, and then we'll start sharing it. Just a second. You should see it there. Know what that one's doing.
Yeah, you probably want to share this one. Try this one.
Okay,
Is it?
I think that's.
And then go back to this.
I think
one.
that's it.
You got it?
Yeah, that might be it.
Okay, we got it. Is that seeing it now?
Yes, the changing slide.
Okay. I'll leave you.
Okay. Well, we're missing something on Riverfire. Sorry, I mustn't do it here. Just to change the slide, I just click this. Is that right?
Speak loudly, David.
Okay. I had to go back to the beginning with trying to understand how Bravespan was working with the broadening function in it was working to actually determine wavelengths and then velocities. So is that, can you people online see the mouse pointer moving on the screen? Can you see the red spectrum?
Yes.
Sodium lines? Okay. So this is the typical sodium spectrum, but they're not two clean lines for the primary star. And the secondary star, its D2 line doesn't look too bad. The D1 line is hidden in here. But what this shows is that the wavelength for the D2 line of the primary star 1, that's the wavelength there. And there's another side to the spectrum. There's a gas stream that's coming obviously from the secondary star. So those lines were very broad. And this blue line shows what the Raystein, the first iteration that I did was picking up, that it was finding the middle of that. And basically all the velocities that I calculated were a bit too slow. So instead of 40 something, it was actually the velocity given by this line was 56 kilometers a second. And I also used then the hydrogen alpha line, and I looked a whole range of spectra and saw that the same thing. So the gas stream for that particular time, that was March 28 in 2021. There was definitely a gas stream coming from the secondary star. So those are the results that I got then from an analysis of the whole set of radial velocity curves. So the velocity of the primary star, that's including adding 15, not 22, velocity for the systemic velocity. And this was minus 175. And that gave a very good fit to just about all of the lines. But the key thing is that line there. That's the helium, neutral helium 5876. And normally that line is not very strong. There's an example from towards the end of the time that I was observing it, very weak. And the equivalent line, the 6678 helium-1 line, were fairly weak. But going back 1 month earlier, February the 27th, this line was extremely strong, very strong. And that meant there was a huge amount of material being thrown off that secondary star. And I didn't have radial velocity data for that because that actual night, I'd asked for 2 nights and most of them were clouded out. It was only at 3 a.m. that the clouds moved off, and I was able then to start up the observatory. We had to do everything manually then. So online, we had to open the observatory, get the telescope lined up, get it pointing and so on. So I had only a short time before astronomical dawn to do a couple of observations. So these were 2 30-second observations. And I used the 3000 grating for the blue spectra because the aim at that stage was just to get the spectral type. And we need that for the modeling to get the spectral type of the primary star. Anyway, it was really interesting to see that very strong line. So it meant that the secondary star was very active. And similarly, if you compare that with the one I just showed with the 6678 line, it's very strong. So that means that what that is showing is an impact on the primary star. So you get those very strong lines when there's either a very hot spot or there's material actually hitting the primary star. So the next thing then was I went over all of the spectra from those dates and calculated the equivalent widths. So that's a way to quantify the changes. So the equivalent widths of the helium lines were very strong in February, and then a bit weaker in March, then going down, and finally at the end of May the 26th, they were just not detectable really, or very weak. And what that then did to the radial velocity calculations, these were in late April when there was obviously no impact. So the radial velocity program showed a good fit. This blue line is where the radial velocity of the primary star had actually agreed quite well with the broadened function of the whole thing. And going back to that March the 28th, the line was offset. So the broadening function was showing a velocity a bit less than that of the actual primary star. And then 24th of April, where there was still a fair bit of material coming from it or hitting that primary star, was quite a big displacement. So what that meant was there was a lot of material that obviously coming off that star. And I was in the first round of discussing this with our colleagues in Greece, Alexis, and Ahmet in Turkey. Alexis wrote this little email, and he said that it's really exciting because the eclipse timing variation, and you've heard Roy talk about observed minus calculated, so that's what he was doing, did a quick run on eclipses going back 100 years with this one. It was first observed 100 years ago. And having a magnitude 9 star meant that even some of those early plate studies of time and so on could be quite useful for getting a change of eclipse times. And so the period has definitely changed in that time. And as Alexis calculated here, it's throwing off a mass from that star onto the primary, which is about 10 times more than a typical Algol star. And an Algol star is one where originally the primary star was the most massive. It evolved very quickly, threw off most of its mass, which with a very close binary was mostly grabbed by the secondary star, which then itself increased up into the main sequence and is currently the more massive star. So we've still got more work to do in working with the modelling of that, but it's an unusual system. And if I'd known before I started analysing this that it was going to be like that, obviously I should have done a lot more observations going back. But that May 2021 was the last time we actually observed with the telescope. And we couldn't do it now. If we wanted to get time on that now, we would actually have to pay, I think it's several $100s an hour, and just give ANU what the time that we want something observed. So as observers, we can't go and do the observing ourselves anymore. So that was a really interesting period going back to actually operating the observatory, the telescope, the spectrograph, and collecting the data ourselves. We can't do that anymore. And for me as an amateur, it was the observing that was the interesting thing. Working out the theoretical side of things is where our professional colleagues are involved. So anyway, that's what I've been doing. It's been keeping me really busy for quite a while, and it will continue to. So thank you. I've just finished with, this is sent to me by, hang on. Is this going to go? There we go. This was just an animated model that a colleague in Thailand, David Krishan, a Ukrainian who's working there at the moment, and I'd sent him data on this star, GQ Triangulum Australe. It's somewhat similar to the one that in UW Virginis. And they've actually done a modelling, calculating mass transferring from the primary to the secondary. So it shows the sort of thing that was probably happening with this one that I've just been talking about. And when you look at these diagrams here, you can see that depending on the phase, orbital phase, when the impact occurs from the secondary onto the primary does change with phase. So sometimes it's in the first quadrature, you know, that very first night in February 28, it was in phase 3.3. And later on, it was more prominent at around phase 0.7576. So it's similar to that, but of course I don't have that sort of model now for that one. So thank you.
Thanks, David. Thank you very much. Okay. Well, I think we have two more people who'd like to present briefly. Roy in the lecture theatre here, and Renato, who'll be presenting online. So, Roy, I think you mentioned you thought we'd already put your presentation on there.
I think it's called Roy Barstows.
It's not on there.
It was that green.
Nick, while you're getting that up, can I make a quick announcement on behalf of Chris Ryan? So our astrophotography director is online today, but he's on a computer without a microphone. So he's asked me to remind everybody that the astrophotography competition entries close on the 19th of September. That's just a little under 2 weeks from today. And the rules for entry are in the presented in detail in the July newsletter.
Okay, so thank you. So thank you, Chris. I'm sorry you can't speak to us directly, but I'm sure people will want to mention they'll think of the astrophotography competition. While Roy is getting his presentation, Renato, how long is your presentation?
Just a couple of minutes.
Why don't you start that now, and then I'll be adjusting by getting Roy's presentation on as soon as you've finished.
Sure, thank you very much. So if you don't mind, I'll share a screen.
Yes, it should be set up for you to do that.
So can you see a light curve?
Yes, I'm just letting Renato go.
So,
Okay, we'll get Renato.
Okay.
Yes, I'm doing it.
I think I got the wrong one. Let me try this again. Sorry for that.
It's all right.
I have to start at the beginning. I just tested it before. Great. You see my light curve?
Yes.
Yes.
Very good. So last month, finally the heavens cleared a little bit and the weather played along. So I would have had 6 occultations on my list. But unfortunately, the last week of August, I had to go to Kumara to build a communication center for the ambulance. So I was away for the whole week and I couldn't do anything. But I had luck. In the previous weeks, I had 3 occultations that I put on. So we see here, the first one was on the 4th of August, which was asteroid Pipa. Also occulting a fairly faint star, and we had a really nice light curve associated with it. Then a little bit later, I had Ortrud occulting even fainter star that was about 15th magnitude. And as you can tell here, this is a very unusual area. Can you see my mouse? So this is the area where the occultation happened. But what I did is I actually used a function in Tangra that can actually bin associated slides together. So this image here was binning 6 frames and adding them up to each other, and lo and behold, the asteroid comes out much better. So the only thing that I needed to do is I needed to be careful about which which measuring points I'm using to define the disappearance and the reappearance. But if you compare it with this, you can see it's quite a bit of a difference. So, and the last one was on the 16th of August, another nice one with a sharp drop. So this is about, I think, 2 magnitudes drop in brightness for where the star went away as soon as the asteroid came into it. Anyone have any questions?
Okay. You were altogether too clear, Vanessa. Thank you.
Thank you so much.
Thanks very much. I'll just swap this over and see if we can pop your presentation up, Roy. Need to just swap them around because I can't run them. Actually, I can run them simultaneously for a short while. Just a second. We'll see if we can pick it up. Yes. There we go. Okay, this is it, isn't it?
That's it.
I think we started the slideshow first. We'll do that. And this one. Okay, and I'll just see if I can go into Zoom and get you going. There's a share. Somewhere in here, there it is. That's your one, isn't it?
That's it. Yeah.
What we need to do is, can those online tell me if you can see Roy's presentation?
I can see it.
Yep.
How do I change slides?
That's what I'm just doing. Okay. I hope. No. That one. Here we go. So you can now go. Okay.
Yeah, we're seeing the slide change.
Great. Thank you.
I just use these buttons there.
Those buttons.
I'd just like to talk to you about some contemporary photometry for doing contemporary software for doing photometry, and I'm using Forenso as an example. It's an acronym which stands for Photometric Reduction and Analysis Software, and it really is quite amazing what it can do. Last month I talked to you about some of the resources that the American Association of Variable Star Observers has, including these that you can see here. Forenso actually uses these three resources, which are marked with red rectangles. It does so seamlessly for the variable star plotter, which brings up charts of comparison stars from which you calculate the magnitudes of the variable stars. The variable star index, which in fact contains the information about the variable star itself. And with one click in Forenso, you can upload your report to the AAVSO website. Your report will generate a light curve, and I'll be able to show you just how to do that. The author of the software is Tony van Munster, who lives in Belgium, a very experienced photometrist. He was also responsible for the software Forenso, which has been around for many years. It's well known by photometrists and is a light curve and period analysis software. Like any software, Forenso requires you to set it up properly. For example, and I won't go into a lot of details, this is me. ARX are my observer initials, which I've had with the AAVSO for over 20 years, and here's my geographical location. You need to set up astrometric and photometric catalogues so that the software knows what catalogues to use. APAS DR10 is the AAVSO Photometric All-Sky Survey, data release 10, and from that photometry is determined. UCAC4 is the 4th United States Naval Observatory CCD astrographic catalogue, a huge catalogue of enormous numbers of stars. Once you become proficient in photometry, you can correct for the way your system sees the colours of stars, and for that you need transformation coefficients. For B and V filters, the closer this number is to 1, the closer your system represents a standard. The closer these numbers are to 0, the closer your system represents the standard. The actual figures allows the transformation of your data to precisely match that of the correct professional photometric data. The software allows you to capture or create master darks from your original darks and master flats from your original flats. You have a blank screen area here. You simply add the files, click Create Master Image, and it happens within a few seconds. The master files are saved within a folder called Calibration Group Selection, and the software will calibrate your science images. It does all that very quickly and easily. For example, I'll show you the field of V676 Centauri, which is an eclipsing binary star, spends most of its time in 12th magnitude, and it has a period of about 7 hours. The basis for any observing within this software is that you need to set up an ID card for each variable star that you observe. That's the name of the variable. Once you've got that name there, you click AAVSO lookup, and this is where the integration with the AAVSO tools occurs. Once you do that, it recognizes that it's an AAVSO variable, which has this index number or catalog number here. or the database number really. It picks up a chart that matches the field of view that you use for your particular images and gives you the position of the star. What you do next is to add your FITS image, an image that you've captured for this field, and it displays on the screen. And within a few seconds, astrometry will be performed. The RA index of every pixel on that image will be known to the system, and it puts on the screen the variable star, the AAVSO comparison stars, and comparison stars from UCAC4. It's magic the way that happens, just seamlessly without you even having to think about it. So what you have at this stage is the variable star marked with the purple circles. The comparison stars with the numbers beside them are the official AAVSO comparison stars. And it's that information that enables Forenso to do its photometry so quickly and easily.
You have to give a reverse image to the software? Can you take
I can't hear you.
You have to give the software a reverse image, or can you give an image with a black background?
Oh, it can be, I think you've got a choice. I think it's a setting. It's one click. I think the question was about the reversed image that I'm showing on the screen, and Roberto asked if you can use an image that is not reversed. And I think that's just one click in Forenso to decide which way you want to see the image. It's totally immaterial. On the other hand, I see what you mean, that you wouldn't see those. So this is the way the image is presented in Forenso.
Right. No, that's easier to see, I guess, because you've got those green circles and purple circles.
Yes.
It's easier to see on a reverse image.
Yes, yes. I think Roberto's point was with a reversed image, you can see all the markup quite readily. Is that right? Yep, okay. So those comparison stars that you can see there, if you take note, there's a 121, 135 and 127. That means that these stars have magnitudes of 12.1, 13.5 and 12.7. The corresponding AAVSO chart, the actual chart itself, is here, and those particular stars are shown on this chart. That just simply shows you that it's actually using an AAVSO chart. If you hover the cursor over the variable, it will show you the information about the variable, including what type of variable it is and its period. If you hover the cursor over a comparison star, it will show you the photometric information for that star. If you right-click a comparison star, you can choose it to be a reference star, which in Forenso terminology is the type of star that enables the magnitude of their variable to be calculated by comparison. If you right-click the star that you want to be the check star, in other words, a star that is constant, and you just need to know that your system is showing that as a constant magnitude, indicating that everything is working well. So what you have at this stage then is your variable star, a reference or comparison star, and a check star. And the next thing to do is to run the photometry. This screen is set up with the particular calibration files that you wanted, the folder with the science images, and the controls are down the bottom. To start the photometry run, you simply click this arrow here, and I use 10 megabyte files. It does photometry, it does astrometry on each file, and the photometry at 2 seconds a file. So it's amazingly fast. Once the photometry is finished, you can display a light curve with the little light curve icon in the second red circle, and you can display the report that goes to the AAVSO by clicking the icon in the red circle to the right. And that's what the light curve looks like, with the variable star, the check star in blue across the middle, and the reference star constant down the bottom. I don't think I can show it here, but near the top left, we're still in Forenso in this particular screen. Near the top left, there's an icon which you click And one click on that immediately displays the light curve in Parenzo, which is Tony van Munster's light curve analysis software. It's an eclipsing binary star, so you need to know the precise time of the of mid-eclipse. For the prime, a few mouse clicks gives you the region of the light curve you want to measure, and then another click gives you the actual time of the mid-eclipse. For the secondary eclipse, the same thing. A few mouse clicks gives you the information that you need. This is the report that's automatically generated that can be sent to the AAVSO, and you simply open it up in the folder, and one click and it is sent to the AAVSO website. If you go to the AAVSO website and display the light curve that this data will produce, this is exactly what you can see. So that's it. This software allows the easy creation and saving of your calibration files. It does calibration of science images quickly and easily. It integrates seamlessly with AAVSO tools for photometry and astrometry. There's automatic photometry with display of light curves and the creation of the reports. And you can submit the report via the AAVSO website. Well, you don't submit the report via the AAVSO website, you submit it from Forenzo. And what you can see is your light curve when you go to the AAVSO website. And there's one-click integration with Forenzo for light curve analysis. So there are no difficult things that you have to do. You simply have to learn how to run the software. If anyone's interested, I'd be happy to talk to you. I'd be happy to give you a demonstration using Zoom. And if you want to get into photometry, I believe this is the way to do it. Thanks very much.
Thanks, Will. Yeah, thanks very much. That was that's some very impressive software, isn't it? Is that written by the AAVSO?
Now, the author of the software is Tony van Munster, who's a very experienced astronomer and photometrist from Belgium.
Oh, thank you. Thanks very much. Well, thank you. Indeed, I think it's all the section directors and tabling of observations that I've had been alerted to. Is there any general business anyone wants to raise? Okay, in that case, I'd just like to apologise again for our somewhat chaotic AV. It came as a surprise to Roy and I to find this is not our normal lecture theatre for those online. We're in the lecture theatre next door. It came as a surprise to find not only was the computer not working in the main lecture theatre, which controls all the displays, but that the power wasn't either on the desk. So that caused us a slight difficulty. So we, with the help of security, moved to this lecture theatre, which is next door. For those in here will know that already. But and having come here, the power was at least working, but the computer here wasn't working either. They must be doing some upgrades in the background. And so I'm afraid we've been a bit clunky because we're having to use my laptop to do everything that you'd normally do on the main computers, and it hasn't got that many connections on it. So it's I'm hoping we'll be back to normal on the AV front next month in October, and back in our normal lecture theatre, assuming that's working well. So thank you, everyone, and thank you for the presentation. Looking forward to seeing you in October, when, of course, we will have I believe, our astrophotography competition at that time. So, and also for those here in the room, the supper is on with the library, where Jackie, I think, in the tea room round the corner. If you don't know where it is, follow everyone else, and you'll soon get there. So yes, thank you, Chris. That's great. So thank you, everyone. I think Joe may well facilitate a further discussion for those who'd like to online, but my laptop is looking very relieved to have the system being switched off here at this end, and I'll do that now. Thanks, everyone. Have a good evening.
Thanks, Nick. Yes, I will host a post-meeting Zoom chat. I'm just going to end the recording now.
Great. All right. Well, I'll leave here at this end. Thank you.
Thank you.